I think we're ready to start. Thank you all for joining us for this session on algorithms and of the Maple Conference 2025. Without further ado, I'd like to introduce Dr. Stanislav Barton. Dr. Barton, the floor is yours. If you could share your screen. Yeah.
Thank you.
Great.
Hello to everybody. My name is Stanislav Barton. I am Professor of Informatics in Opole Polytechnic University. And during COVID epidemic, I was asked by heads of Opole Voivodeship to help predict count of new sick people. So I used Maple for prediction. This prediction was based on usage of Gompertz function. This function is very, very old and still very nice for such things. This function is heavy nonlinear, so to use this function as a regression function, it's necessary to use Gauss-Newton iteration method. So maybe you can see on my screen, this was solved in Maple 13 because it was necessary to produce a lot of graphs to support my computation, and in Maple 13 is very good interface into PostScript, and from PostScript transfer files to any other documents like LaTeX or PDF file. It's very simple. So when I started to solve this problem, I got data. Here is part of this data. You can see here. It's count of sick patients from the beginning to end of epidemic. But when I was asked to help, it was 72 days after breakdown of the epidemic. So my data looked like this. It will be better to see from this screen. Do you see it? On the vertical axis is days from beginning of epidemic. On the vertical axis is count of new sick people. Dots are data which I received from Polish epidemiology services, and sick line is 7-day rolling average, because this data was not sent every day. It was sent, let's say, every second or third day. That's why it jumps up or down. So for the prediction on the beginning, I used Gompertz function. Gompertz function is this one. And this function is very good for computation or illustration of total count of sick people. It means from the beginning epidemic to end of epidemic. But for daily incomes, it's necessary to use time derivative of this function. It's here. This function contains 3 unknown parameters, G1 to G3, and it's very nonlinear for these parameters because it's double exponential function, you can see here. So to estimate values of these components, of these coefficients, is not simple. It is necessary to use Taylor expansion for linearization with respect to coefficients G1 to G3, and on the beginning of epidemic is the best to compare it with exponential function, which is much more simple, this one. But this exponential function contains one nonlinear coefficient 2. So for both was necessary to use linearization and to convert it into Taylor polynomial for linearized coefficients. For exponential function is here, or for Gompertz function it's done here. You can see that it's not too simple. dg1, dg2, dg3 are corrections for unknown coefficients g. in exponential function, there is only one correction. And after that, it's necessary to build something like, it's not exactly, but very similar to Jacob matrix containing derivatives. And rows of these matrices corresponds to daily counts of new patients, and rows corresponds to coefficients which we are looking for. Here is iteration for exponential function and demonstration how fast is convergence. You can see that it converges quite fast. Here is final exponential function for beginning of epidemic. And resulting exponential function for beginning of epidemic plus prediction for next week, plus minus estimation or accuracy of prediction. You can see that this correction is quite good. If the same is done for complex function, problem is that it's very hard to estimate initial value of coefficients. So from hygienic service, it was possible to say to receive information that from beginning of epidemic to end of to peak of epidemic, there may be interval about 15, maybe 20 days. So let's assume that peak maximum must satisfy some condition for second derivative, and from this it's possible to determine that if we will expect that maximum will be in day, for example, 90 or 110 from the beginning of epidemic, that it's possible to estimate values of other coefficients, but these coefficients are still necessary to compute for nonlinear equation. So to solve this nonlinear equation, it's the best to plot function describing how depends solution of these three equations on this one coefficients, and it's possible to determine that coefficient G1 may be somewhere close to -12. It's possible to solve it using Newton iteration method. Maple is fantastic for that. So initial function may be something like this. And after that, it's possible to use these initial values of coefficients and to start Gauss-Newton iteration method. I jumped a little bit more ahead. So to be more precise in prediction of these coefficients, I tried how many sick people must be in maximum. So I began with that day 110 from beginning of epidemic, and I assumed that count of sick people will be somewhere between 4,000 and 5,000. I found for that the best value of all coefficients, and around minimum of this function I made a small step around maximum, and till that I found that it's possible to expect that maximum of sick people will be about 1,600 people, and it will be in day that 110. So this may be used for estimating of initial value for Gauss-Newton iteration, and this iteration was successful and returns such convergence. There are two convergences. One is if I use numerical precision 10 or 18. 10 is not sufficient, so with precision of 18 digits it converges much faster, because thanks to very nonlinear function there is a big accumulation of rounding errors, and it's solved if you use a higher numerical precision. You can see that converges for a higher precision much faster. So final Gompers function you can see here. It is this one. And comparison of both functions is here on this screen. And as you can see, there is no main difference between prediction based on exponential or Gompers function. It means that on the beginning of epidemic, it's much simpler to use exponential growth and to try to estimate values for Gompers function if rolling average will fall down below exponential prediction. It means Gompers function can be used if you will be close to point of break. It means somewhere close to inflex point of time derivative of Gompers function. Here you can see the same for prediction, that difference of prediction between exponential function in blue and Gompers function in dark green is not big. It's big. It's small as uncertainty of sick people. And there is a difference between prediction in exponential and Gompers function. You can see that it's very, very small. So for prediction in as epidemic continuous, it's the best to use more than one wave. So initial values for other waves will be estimated using the same method. And at the end, it was possible to see that epidemic occurs in 3 waves.
We're at 12 minutes.
Yes, here are data for whole time when I solved epidemic prediction. And here is corresponding worksheet, preparation of data for prediction for Gauss iteration method. It's quite complicated. Results. And here is final graph, which I every week send to heads of voivodeship, including similar graphs containing 2 districts in Opole voivodeship, comparison of one voivodeship with other, and so on and so on. Thanks to this prediction, it was saved many lives because Opole voivodeship was the best ready for new patients. Thanks to that, we had enough time to be ready and to gain material, respirators, and so on. And this is real result of this work. I got award of Opole Voivoda. So it's all, and it's only very small part from work I did. And here is shown how it's disassembled, that prediction from 3 waves. You can see these 3 waves. And it's all from my side.
Thank you very much. That's a wonderful presentation. Thank you very much. I would like to open the floor for questions.
Would you like to receive this worksheet to present it somewhere or to convert it to some publication or no?
I think the Maple transactions is our open access journal, doubly open access, free for authors and for readers. I think they would be very interested in receiving this as a contribution.
Okay. I shall send you that worksheet and we can be in contact by email how to continue.
That would be wonderful. I had
Okay.
one question I wanted to ask in the 30 seconds we have left. the intervals you showed around the predictions were those like confidence intervals, or are those standard deviations, or what was the
Yes,
nature?
it was standard deviation.
Okay.
Standard deviation computed from mid values.
Yeah, understood. Thank you very much, Dr. Barton. And we continue with Dr. Tomas Recio. Dr. Recio, the floor is yours.
Okay. Okay. So thank you for allowing me to come here to explain a little bit about something very, for me, I am quite old, for me it's very impressive. This is my own work together with some other colleagues. One of them is Pilar Vélez, which is, I see her in one of the persons in the audience. We are both from the University Nebrija in Madrid, and also this is work together with Zoltán Kovács from the University College of Education of the Diocese of Linz in Austria. And we are going to present a mixture of some program and Maple. So it's a combination of the two. So first of all, let me talk about the underlying program, which is called GeoGebra Discovery. So you know GeoGebra, maybe you know. GeoGebra is a very popular, free, widely available software for dynamic geometry and also computer algebra. That's why it's GeoGebra, geometry and algebra. So it's a program that has around 100 million users all over the world. It is translated to 70, 80 languages. So it is very popular with more than 1.5 million resources, public resources for use in the classroom. So it's a very important program. And GeoGebra Discovery is a fork version of GeoGebra that has expanded automated reasoning features. So GeoGebra has some automated reasoning features, but GeoGebra Discovery has expanded version. So for instance, GeoGebra automatically gives you the truth or the failure of a statement. You declare, I don't know, Pythagoras theorem. You construct a right triangle and you declare that the hypotenuse square is equal to the sum of the square of the legs. Then GeoGebra says, yes, it is true. And that's all. With GeoGebra Discovery, you can see the algebraic proof of this statement. And there are other expanded features. As I say, GeoGebra Discovery, it is free as GeoGebra. Also, you can have it in different versions, off and online. You can work with GeoGebra Discovery on a mobile phone, on a laptop, on a computer. So it is very widely available. You can download the current version here in this web, and there are many commands for automatic reasoning: relation, proof, discover, show proof, locus equation. I will talk a little bit about them later. And one of the special features of GeoGebra Discovery that doesn't have GeoGebra is that you can copy the computer algebra window as a Maple input. So we usually work with GeoGebra Discovery, and if we have something to deal with that GeoGebra Discovery is not ready to work with, we copy the CAS window of GeoGebra Discovery and we put it in Maple, and we work with Maple trying to solve the different problems. So this is GeoGebra Discovery. And these are two important, two clear references. One of them is very recent, is published in January 2025, and it is the show proof command. It is published in a journal that is not free. So I have added here a link for the presentation we have done in this conference. The conference was International Symbolic Symposium on Symbolic and Algebraic Computation, the ISAC. So this is the presentation, and you can see the presentation. And of course, if you are a member of the ACM, you can take a look at this paper. And then there is a chapter of a book in which we present, globally speaking, the automatic reasoning tools in GeoGebra. And you can see this book has been published by Springer concerning mathematics education in the age of artificial intelligence, and you can find the digital object identification in this way. So what is the goal of our talk? So the goal of our talk is the following. Suppose I give you a theorem like this one. Given an equilateral triangle, the altitude from a vertex divides the opposite side in two equal segments. So this is a statement. I make the construction. This is GeoGebra discovery. I make the construction. This is an equilateral triangle. I make the perpendicular. This is point D, and I want to prove that J is equal to K. So this is the cast window, and this is the statement I am going to prove. And the machine starts doing the proof because it says it's correct. So start doing the proof. This is the kind of proof you can see. It's purely algebraic proof. It computes equations, equations for the fact that this line is perpendicular to this one, that the fact that this is an equilateral triangle. So all these are equations. The point A has coordinates V1, V2, point B, V3, V4, point C, V5, V6, etc. So all these are the equations. And then make some simplifications, like point A will be 0, 0, point B will be 0, 1, without loss of generality. So this is the simplified version of the hypothesis. And then this is the end of the story. Then the machine tries to see whether the hypothesis equations plus the negation of the thesis is, of course, an equation, the negation of the thesis is empty, is an empty set. So we want to prove whether negating the thesis yields a contradictory result. So finally, what the machine does using some Gröbner basis computations is consider all the hypotheses. The S are the hypotheses. The last S, the S13, is the negation of the thesis, and the machine says, okay, this is 1, and because the negation of the thesis will be 0 and the hypothesis will be 0, this is 1 equal to 0, so it's contradictory, so this theorem is true. This is the way the show proof works, okay? So let me do it in a little bit quicker way. These are the hypotheses. This is the negation of the thesis using a dump variable V17, and then the machine casts, the Gröbner basis computation finds an expression which is equal to 1 and equal to 0. So this is contradictory. So now we take this last expression, the sum, we take this last expression, which is the combination of the thesis, the hypothesis, and the negation of the thesis equal to 0. Because, of course, if you know that the negation of the thesis, you do some operations and you get the thesis as a combination of the hypothesis. So this is the output of GeoGebra discovery, the thesis as a combination of the hypothesis. So now what we are trying to do is the following. This is one statement. The statement that says in a equilateral triangle, the altitude goes to the midpoint of the opposite side. But now I say this is ridiculous. I can do the following. Instead of taking this, let me go back here. See, here you have this combination, and you see that S4, S3, which are hypotheses, do not appear here. So that means that some of the hypotheses are not needed. So we can automatically find a new theorem. The new theorem is that you do not need the triangle to be equilateral. You you do not need to use S6 or S7 because it has a 0 multiplier to derive the thesis. So that means that the theorem is true for isosceles triangle. So I have found a new theorem only by observing this list, this expression of the thesis as a combination of the hypotheses. Or this other second derivation. So in this second derivation, I decide that I am interested in finding S12 as this S12 as the thesis, and for me the thesis will be a new hypothesis. So I reformulate this expression, putting S12 as the thesis and the thesis as one of the hypotheses, and what I get is exactly something like an obvious statement, because funnily this coefficient here is already a consequence of the previous hypothesis. Or let me try to do quickly this new statement. This is what we call in Spanish the Thales theorem. So these are the midpoints, D and E are the midpoints, and I say these two lines are parallel. So I want to prove it, and I obtain some expression like this one, and now instead of taking this expression, I take S2 as the new thesis and the thesis as part of the hypothesis. So what I get is something like the converse of the Thales theorem. So just with one expression that I get at the beginning, I can derive a lot of new results, like the converse of Thales theorem, which is true. Or sometimes theorems of high complexity, like this one, I am not going to go into details, like this one, this is statement of complexity 13. Look, complexity 13, which is a very high complexity. So we have a machine, we have a protocol that obtains a lot of new statements. From one given statement, we derive a new statements. Some of them are very difficult, some of them are converse, some of them are trivial because what I am looking for was already part of the old hypothesis. So this is for us ongoing work because it opens the door to reason automatically about geometry with like a machine, like an artificial intelligence machine. Let me say that the difference with artificial intelligence and what we do here is that what we do here is rigorously true. It is not statistics, it is logic. So we are doing algebra, and you know the model of computation is precise, is rigorous, it is not approximate. And what we do is
we're at 12 and a half minutes.
Yes. So all what we do here, all that I am doing here, all these derivations, I am checking that they are correct. I am checking them using Maple because right now GeoGebra Discovery is not able to verify statements that are expressed only algebraically. So some theorems are difficult to interpret geometrically, some are very interesting. So for us, it's very surprising work. With one statement, we can derive a lot of new ones, and they are all correct. So I will say that I will share with the organizers this presentation. And here in this Dropbox, we have a Maple file where the whole computations are much more clearly explained. And these are some basic references, as I mentioned before. This is inspired by this theorem, by this paper, Heuristic Strategy for Geometry Theorem Extension. But of course, ours is not heuristic, ours is rigorous. And this is all. Thank you so much.
Thank you, Dr. Recio. I want to open the floor to questions.
Thank you.
If there are no other questions, I wanted to ask, you showed the complexity of the statements at some point of the proofs. Does that map in a direct way to some property of the Gröbner basis computations?
Of course, you know, you know a lot. Yes, all what is behind this is Gröbner basis computations. and it's a lot of it is a lot of open questions about Gröbner basis. So what we do is we take so the hypothesis is an ideal with generators. We compute the normal form of one with respect to this ideal, and we express this Gröbner basis in terms of the given generators.
Yeah.
So we do all
Yeah.
this process, and the on the polynomials that you need to obtain to multiply the generators to derive the thesis, this is for us the measure of the complexity. That is
I
how
see.
difficult, how new is the thesis with respect to the given hypothesis.
Yeah,
So
understood.
this is
Thank
our
you.
measure.
Thanks. Yeah. With that, we'll end this presentation. Thank you again, Dr. Recio. And the next presentation will be by Dr. Uzma Shafiq. Dr. Shafiq, the floor is yours.
Thank you. Good morning, everyone. My name is Uzma Shafiq. My work is on the role of reinforcement learning and explainable AI for S-pair selection in Buchberger's algorithm. I'm doing this work in collaboration with Dr. Matthew England and Dr. Nair Zaidi. Before I start my talk, I do want to mention that this is an ongoing research, although I would be presenting some promising results. However, there can be better results in the future as well. I'll start off by introducing a little bit about Gröbner basis. Dr. Recio just mentioned about Gröbner basis. So it is a special set of generating. It is a special generating set for a polynomial ideal. Mostly, it is used in computer algebra, in robotics, coding theory, and cryptography. So my PhD, so I'm in second year of my PhD, and my PhD is mostly focused on Buchberger's algorithm, basically optimizing Buchberger's algorithm. So I'll introduce Buchberger's algorithm a little bit. It is an iterative process, and we start with a generating set, a set of polynomials, and initially we have the basis as that initial set of polynomials. If we look at the different steps that are involved, the first step is that the most crucial step basically is the selection of the S pair. After the selection of S pair, we compute the S polynomial, and then we try to reduce the S polynomial. And if it is reduced, well and good. But if it doesn't, it gets added to that basis itself, and in that way, the basis keeps on growing. Eventually, we do end up in a place where all the S polynomials are reduced. So the key insight here is that the step where we are selecting the S pair, it does strongly influence the number of reductions, the size of the intermediate polynomials, and the overall runtime. So as you might be aware that in worst case scenario, the computation of Gröbner basis is doubly exponential. And to my knowledge, there has been only one study that uses artificial intelligence to optimize Buchberger's algorithm. Dylan Pfeiffer in 2020 basically designed the problem as a sequential problem, and being a sequential problem, it was a very good for reinforcement learning. He treated the computation of the Gröbner basis as the RL environment, and he tied the reward that the agent was learning to the number of polynomial additions that were performed in the reduction of that pair. Some of the core components that we need to note here is that the policy that was being learned, the input to that policy was called the state, was the exponent vector of the current basis of the S pairs and the S pairs. So by exponent vectors, I mean you have the exponents for the variables that are present within the initial set of polynomials. Moving towards the findings and limitations of Pfeiffer study. So Pfeiffer does find out that RL agent does outperform the classical selection strategies. So these strategies, so the comparison he draws is between degree selection, sugar selection, normal selection, and first selection strategy. In his study, he found out, he reported some behavioral insights that he got from a non-exhaustive manual analysis. Agent mimics the degree heuristic. The second one that he mentions in his paper was that the S pairs that are monomials are preferred as compared to the ones that are binomials. And the third one was that S pairs with lower degree are preferred more as compared to the ones that are of higher degree. The limitations of his study, one of the most crucial limitation of the study was that the study was limited to binomial polynomials only. The reason that he worked with binomials only was that, so when we reduce the intermediate S polynomials, those would be binomials, and after reduction, either you end up with a binomial or a monomial. But with higher polynomials, with more number of monomials, you cannot really predict that the intermediate polynomials would end up with 2 terms or more number of terms. So that is a restriction and a limitation that he had applied in his study. The other thing was that the training of the policy was based on the exponents only. He does not take into consideration any features or even the coefficients as well. The third factor or limitation in his study was that the policy was not interpretable, although he does provide us some insights, but these insights are based on a manual analysis. So the first objective of our research was that we wanted to extend Pfeiffer's policy for higher degree polynomials, not just for binomials. What we did was that we only used the first 2 terms for the higher polynomials. By higher polynomials, I mean it can be trinomials, it can be polynomials with 4 terms or 5 terms, and so on. So we use only the first 2 terms with respect to the monomial ordering, and that are used as the state, as an input to the policy, and then the RL agent is trained. After the RL agent is trained we have the policy, we do explain the whole policy, how it works using a surrogate model and sharp analysis. If we look at the results here, you can see, so the blue bar charts are the results that Pfeiffer has also reported. So the results are reported in percentage improvement from degree selection strategy. You may wonder, why do we go for the degree selection strategy? Because out of all the classical selection strategies, degree, sugar first, and normal, degree was the one that performed best for Pfeiffer, and in our case as well. So we calculate the improvement of our results from as a base, keeping the degree selection strategy as a baseline. So you can see in case of binomials, you see the improvement, but even for the polynomials, the orange bar graphs are for the polynomials that had higher number of terms. You can see that we do achieve some improvement, and we can say that the policy that we trained is generalizable. In the chart, you can see that the last 2 bar charts, these are some new selection strategies. The true degree one is the one that Pfeiffer has reported, he found out in his study, and the one that S poly average degree is the one that we found out after running the explainability part of it. I'll explain the explainability part in the next few slides. But you can see here that it is interesting that we could find a new heuristic, not a heuristic, but a new feature, which when hard coded as the selection strategy did perform similar to what the agent was predicting. Although Pfeiffer also has reported one, the 2 degree one. The next concern here was that whether the RL agent would be generalizing or not. So the RL agent is trained on a specific distribution. So the concern here was that what if we provide a data that is not the exact same distribution? Although there are going to be some constraint on the distribution itself, but the agent was trained on a data that predominantly included binomials and trinomials. But we carried out a testing, we gained a testing data set that would have more variance in it. So by variance, I mean it would be ranging between 2 to 9 terms. It would include binomials, it would include trinomials, and then so on up till 9 terms. If you see the results in the bar chart, we can see that the results are very much comparable, and the agent and the 2 new selection strategies as well, and 2 new hard-coded selection strategies basically perform quite similar in terms of whether this distribution was changed or not. So this does confirm that the policy is generalizable. The other factor that was a very important part of our research was that we wanted to interpret why the policy or why the RL agent was making certain decisions, what were the factors that were driving these certain decisions. So for that matter, we trained a surrogate model that would mimic the RL policy for the selection of S pairs. One thing that we did differently here was that the RL policy had an input of the exponent vector, as I mentioned previously. However, for the surrogate model, we did came up with a set of features, and those were used as the input. So the motivation behind doing that was that the exponent vectors could provide only limited information and not likely to be very useful to us. So the features that were extracted from these exponent vectors would provide us more information regarding the working of this model, or regarding the factors that were driving certain decisions. We further used SHAP analysis. The key findings here were the one that I showed you before in the results. The S poly every degree is one of the most influential features that came up after we ran the SHAP analysis. And when we hard-coded that as a separate selection strategy, it did perform quite well. And as we saw previously as well, if I go back here, it does provide us results that are similar to the agent one. If you look at the orange charts, the first and the last one. There were certain other findings as well that we found that when we extended to higher degree polynomials, so there was one finding that Pfeiffer had reported that S polynomials that are monomials are preferred as compared to the ones that were binomials. So generalizing it to higher polynomials with more number of monomials, so the longer the S polynomial would be, the less likely it is to be selected. There were new factors that were uncovered based on S polynomials that performed similar to the agent, and there were other factors as well that performed better than the agent. So there were two factors. One was S pair based, and the other one was the S polynomial based. If you look at here, we treat the agent as the baseline, and the S pair based is providing around 20 to 23% in case of the dataset that had more variation in it, and the dataset that was predominantly binomials and trinomials, it provides around 5% of improvement. But if you look at the other one, the S polynomial based, it provides an improvement of around 30%, which is quite substantial than the agent. And mind you that the agent was already performing better than the classical heuristics, the sugar selection, degree selection, first selection strategy. Although these are good results, these are promising results, but I do believe that there needs to be further research on this in terms of would these results generalize to more, a different distribution. So that generalizability analysis does need to be carried out. And if one of the major objectives of my PhD has been that using complex RL, ML, or even deep learning architectures, and then integrating those with explainable AI, if I can uncover factors that are very simple or that can be then used without the machine learning models, and we can come up with new heuristics that can optimize these algorithms, that is one of the objectives of my PhD. And these are, I believe, good and promising results in terms of that.
So 12 minutes.
Yeah, just to summarize, the RL agent was already outperforming classical heuristics for binomials. What we found was that it is generalizable to higher polynomials as well. And then with SHAP analysis, we found out new features and new factors that can contribute towards better results as well. I think I'll stop here, and thank you so much for your attention. If you have any questions, I would love to answer those.
Thank you for that wonderful talk. I don't see any questions in the chat. So one thing I was wondering about is, so in your test suite, so you mentioned you have basically two populations that you were looking at, the one with mostly binomials and trinomials, and the one with more terms. How did you make decisions about like number of variables,
Yeah, so I mentioned that there are still going to be some restrictions. So yeah, those restrictions are going to be the number of variables, the highest degree that that distribution can have, and then the number of initial generators or initial number of initial polynomials that are going to be there. So for this study alone, the just taking into consideration that computational power that it takes to compute the Gröbner basis, then just to train the RL agent as well, we did keep it to 3 maximum number of variables. Then the maximum degree was limited to 10, and then we had 8 initial polynomials that are going to be present. So those restrictions were there, but when it comes to the number of terms in a single polynomial, we did not have a restriction on that.
Understood. Thank you for your answer.
There is a question in the chat from Bertrand. Would you be able to tell whether the AI approach would be more efficient or change the worst case scenario encountered in Buchberger's algorithm?
So eventually, the main focus of this whole analysis isn't that we want to replace Buchberger's algorithm with the AI approach. Rather, we want to find certain factors that can contribute towards the improvement of the complexity of these algorithms. For the worst case, I'm not sure if I can improve the doubly exponent. I don't think it's possible to improve that. But for an average case complexity, yeah, if we can find out factors that that can provide us better approach for the selection of S pairs, we can definitely improve the runtime for the whole algorithm.
Thank you very much for that answer. And because of time considerations, we'll move on to talk number 4. That will be Dr. Yagub Aliyev.
So my topic is the dual of Philo's shortest line segment problem and its solution with Maple. So first of all, general information about extrema problems in geometry. So maximum minimum problems in geometry played crucial role in the history of development of mathematical methods. You can read about it in Courant's book, chapter 7, which is here, What is Mathematics? There are other interesting books like Boltiansky's. This is available in Russian, unfortunately, only. The geometrical problems on maximum and minimum, which is part 5 of Encyclopedia of Elementary Mathematics, and Polya's book, which I cannot see myself because of this buttons in Zoom, Mathematics and Plausible Reasoning. Yeah. So extrema problems in geometry are very old problems, and they are very interesting. So the problem that interests me is related to Philo's line. About this line, one can read in this encyclopedic book by Howard Eves, A Survey of Geometry, in volume 2, in entry 13.2.11, there is this problem. Suppose you have an angle, and inside of angle you have a point. You want to draw a line segment through this point so that the endpoints of this line segment are on the sides of the angle, and the length of this line segment is shortest. So this is very old classical problem. It is the answer to this question is known as Philo's line. This problem also appears in the book by James Booth, and not every reference mentions Philo's name. This one, for example, doesn't mention the name of Philo, but it is that same problem. Again, the answer is given. Description of the segment which minimizes the length of line segment is given. This problem can be solved using differential calculus easily. This is a Russian book which solves this problem using the derivatives. The problem was also mentioned in Sir Isaac Newton's classical book, The Method of Fluxions and Infinite Series. This is the book that started modern mathematics. In this book, on page 45, it is this third entry to draw the greatest and the least right lines, which passing through a given point can lie between two others, either right lines or curves. So this is that same problem, and Newton gave this as an example for his method of fluxions. He called differential and integral calculus with this name. This is Russian version, which I have in my library, and you see also the picture of Newton. The interest to this line, Philo's line, comes partly from the fact that it can be used to solve one of the classical problems of ancient world, namely the problem about duplication of cube. Philo of Byzantium solved this problem using his solution for the Philo's line problem. Okay, so I was interested with this problem and thought, why not considering a similar problem, but kind of dual problem. And in the classical problem, you have one fixed point. Why I decided to choose 2 points here. 2 points are fixed. In the classical problem, there are 2 line segments, lines given. In this problem, we have 1 fixed line, and so on. So we have here in the classical problem, we have 2 moving points, E and F. In this dual problem, we have 1 moving point, which is C. In the classical problem, we are asked to minimize EF, the length of this line segment. Here I ask to minimize the length of CD plus CE. So here in this table, you see the similarity between the dual problem and classical problem. This is my first publication about this problem where I couldn't solve it and left it as an exercise or open problem, to be more precise. This was 10 years ago. Recently, I returned to this problem, and using Maple, I tried to solve it, and I'm going to show you my solution. Before showing you the solution of the problem, I should mention that one should be careful with maximum minimum problems in geometry. It is well known that if you assume the existence of maximum or minimum without proving it, you can get contradictory results. This example from Lusternik-Sobolev's functional analysis book is interesting. It says if you assume that there is a triangle with the largest sum of angles in hyperbolic geometry, if you assume that there is a triangle with the largest sum of angles, then you can just prove fifth postulate about parallels. So one should prove existence of maximum before discussing this maximum itself and its properties. This fact is well known among geometers. For example, Hadamard, famous French mathematician, wrote elementary geometry book, and there are some maxima minima problems in this book. And Hadamard, aware of this difficulty, when he asks to solve a maximum minimum problem, in parentheses, he says, assuming that this minimum exists. So he doesn't want his readers to deal with the complexity of this existence part. He just wants to solve them the elementary part. There are several problems like this. Another one exercise 418b, again gives this hint, assuming that a polygon of maximum memory exists. This part, existence of maximum, is not elementary. This requires analysis and hard theorems from analysis. Therefore, he leaves this out of the scope of his book. Existence of maximum minimum, importance of its proof was also mentioned in this book, which I announced at the beginning of my talk by Boltiansky and others. There is another problem with the proof of maximum minimum problems. This was emphasized in the famous classical book of Feierstadt, Laszlo Feierstadt and Gabor Feierstadt. There are two kinds of proofs for extremum problems. Direct proofs, where you have the extremal element and you prove that all the other elements are greater than that, less than, or that greater maximal element, or less than the minimal element. And there are indirect proofs where you have to prove the existence of maximum and minimum, and then prove that that maximum minimum is indeed greater than or less than the others. This book was recently revised by Kuperberg and published recently, I think last year. So the problem that I'm trying to solve is this. We have a line segment and two fixed points on one side of the line segment. We are moving point C1, and we are trying to find point C such that C1 D1 plus C1 E1 is minimal. This is the dual problem for Philo's shortest line problem. And here is the result that I obtained. The minimum is achieved or reached at one specific point, which is shown in this picture. It should be a triangle so that A and B are symmetric to L and M with respect to the centers of these triangle sides. It can be also interpreted as analytic geometry problem. So I wrote it as a calculus problem for minimization of a two-variable function. And here are two possibilities that can arise. One possibility is like this, and minimum is achieved at some point. This is another possibility where minimum is achieved at the boundary. This this study also gave me some other results that I listed here, some interesting geometry facts. This problem can be generalized for some of the powers of those two segments, not just their sum, but some of the powers. And even limiting case, when P is infinity, you get maximum of these two. I solved that
12 minutes.
Yes. This is one publication in Spanish journal about that limiting case. There are open problems. One can study, of course, other values of P, and one can also study the problem when 2 points are increased to 3 and more points, when the line is replaced by a plane. There are many open problems here. Thank you. And possibly I can show you my Maple code, since it is Maple conference. I can't imagine doing this without Maple. These are my calculations in Maple. I benefited from Maple a lot, and thank you.
Thank you very much for that wonderful talk. That was lovely. Do we have any questions from the audience? If not, I wanted to ask the following. So if we look at Philo's original problem, you get the same answer whether you formulate it as the shortest line between the angle or the smallest area enclosed by the angle. That at least that's how it seems to be intuitively. Of course, I haven't proved that, but that seems that should be the case. Is the same true for the dual? Or is that? Do you have any sense of that, or is that?
Thank you for the question. So original question, sorry, I'm trying to find the slide where I have this picture. So original problem is formulated for the length of this segment. So how should one draw this line segment through P so that AB is shortest? But there are other versions of this problem. As you said, one can try to minimize the area of this triangle. One can try to minimize the perimeter of this triangle. These are also interesting problems, and I don't know how one can interpret the dual of these modifications. I only formulated the dual problem for the length of AB. But you are right, there are many other versions of this problem.
There was also a request to give the first reference book that you showed.
This?
Yes, I believe so. Howard is, okay.
What was the question? I forgot. I missed.
Yeah, just to show this reference.
Yeah, it is. Okay. Yes, Courant Robbins, Was ist Mathematik? This is Russian book, volume 5, and Polya's book, Mathematics and Plausible Reasoning, volume 1.
Thank you very much again, Dr. Aliyev. We continue with Dr. Hamdi for the last presentation of this session.
Yes, hello, good morning, everyone. So I will try to share my screen. Okay, do you see it? Is it clear?
Yes.
Okay. So my presentation is on 2-point Padé approximation for special functions. And this work is very much on Maple implementation. But today I will present the theory, and the Maple implementation will be, for example, presented in the article that will follow from this work. So the problem, so this is the outline of the presentation. We will focus today on special functions, particularly the standard normal cumulative distribution function and the error function. So we'll start by presenting interesting integral definitions and relations for the cumulative distribution function, the normal function, normal distribution, as well for the error function. And after that, we will present the idea behind the 2-point Padé approximation, and we'll present application how to make a good approximation that's accurate, but also with a few terms. So it's compact and practical. So the standard normal distribution. So if you have a random variable, uppercase X, random variable, and you are looking for the probability cumulative from 0 to Z, then the definition of the CDF, the cumulative distribution function, would be the integral from 0 to Z of exponential minus X squared over 2. So unlike the integration on the whole domain, this integral cannot be evaluated by elementary functions. So it will involve special functions. And when we teach statistics and probability for students, we still use probability tables. The reason why we are not using a simple formula is that there is no such simple formula to evaluate the CDF of the cumulative distribution function of the normal distribution. So one interesting integral is if we take the square from the left side and the right side, then you will have the product of two integrals that can be evaluated as double integral. And actually, this is the idea of Gauss, how he evaluated the Gauss integral. So also, you will see that this integration is on a square, but it's actually the summation of two integrals on two identical triangles. So summation from 0 to z becomes summation from 0 to x. And after that, if you consider polar coordinates, then this integral will be simplified, and it will take this interesting form. So keep in mind that this integral will be the double of the integral, the square of this integral will be useful for the Padé approximation that we will present later. Now, more about the integrals. So, as you know, the standard normal cumulative distribution function is closely related to the error function. So the two just differ by constant, scaling constant, as well with the simple translation. So the CDF, and this is very classical formula. So the CDF for the normal distribution can be obtained using the error function. So nowadays, when we have Google and we have even on Google, if you type error function, you can evaluate this function. So it's very simple now to evaluate this function. But still, we need a simple formula that can be used in programs, that can be used by students, and that's not very long, with a few terms and accurate enough. So compared to the tables of integrals, we would like to have accuracy up to 4 or 5 digits of accuracy. And of course, the error function is defined by this integral. So summation from 0 to z exponential minus t squared, and with the factor 2 over square root of pi. Now, if you consider that integral that we showed earlier, that involve the square of the CDF of the probability function, cumulative probability function, then we can convert this expression to another similar expression for the error function. So we will have the similar integral. So it will be 1 minus error function of x squared. It will be this integral. And unlike the definition of the error function, which goes from 0 to x, this integral is on particular values from 0 to 1. And the dependence on x is in the expression of the integrand here inside. So the interesting part of this is the integral now is from 0 to 1. The same in this formula, integral from 0 to pi over 4. So unlike the definition of the error function, where the integral go from 0 to z. Okay, so we have that. Now, with manipulation with Maple, so it's possible now to write an expression for the error function at z using a formula similar to the Craig's formula. So the expression would be 1 minus exponential minus z squared divided by z square root of pi times a certain function gz that we can find the expression of it, but g of z is also an integral, so the problem is not solved yet. However, now this form is very well suited for the Padé approximation. So if you do Taylor series and if you do Padé approximation at one particular point, so the accuracy is very good at that point, but it deteriorates when you go far from that point. So the idea is to have a Padé approximation at 2 points, one at one limit, one extremity, and the other extremity. So the idea is the following. So we would make we have the approximation of g of z at z equals 0. So we have this Taylor series representation, and at z equal plus empty, so we have this expression for bigger values of z. Now, the idea is when you use the Padé approximation, so we would like that the Padé approximation will match the expression or series at z equals 0 and as well as z empty. So we try to match at two particular points. One of them z equals 0, and the other one is z equal plus empty. So by doing that, then you have to solve this problem for the coefficient of the Padé approximation, and you will get this system that you have to solve to get the values of the values here of P0, P1 up to P nu, as well for Q0, Q1 up to Q nu. So in that way, we'll have an approximation, a Padé approximation, that's accurate at the extremity at 0 and at empty, and also in between it has still good accuracy. So using the expression of g of z at 0 and g of z at plus infinity. Now, for example, if we take Padé approximation with a degree of the numerator is 2 for the polynomial and the denominator is 2, then you have this expression of the error integral, the error function, where it's very few terms in the numerator and few terms in the denominator, but you achieve an amazing accuracy of 1% of error. So the relative error will be less than 1%. Now, of course, you can go higher order. So if you go, for example, numerator of the Padé approximation of the polynomial is 3 and denominator the degree is 3, then you have a little bit more complicated formula, but still compared to other approximations, it's few terms and you achieve accuracy of 6%. Now you can do the same for 4 by 4, then you will have this expression, which is with this level of accuracy, 0.001%. Now, this idea works for the special function error function, as well for the normal distribution, but as well for many other special functions. And all these approximations and the Taylor series and the Padé approximations are implemented in Maple. And with Maple, it's easy to implement the two-point Padé approximation for all these special functions. So we are now working on the special functions, transcendental special functions, integral functions, such as the Fresnel integral, the Downson integral, and the Euler integral, and the elliptic integral, and the list is long. And this will provide the students with a very simple approximation for these special functions to solve probability and statistics problem with a few terms, because we are using this rational Padé approximation and at 2 points, and we try to match the approximation at the lower limit and at the upper limit. So that's very much about this presentation. So the key is that we are using Maple, and we are using some interesting integral properties of the error function. And as a byproduct of this work, I think I can say I discovered, but I realized there is a very interesting formula for the error function, very similar to the Craig formula. And I think it's new, but we have to check, because it's very classical field. We have to check that this integral formula found by Maple is indeed new, but not rediscovered again. So thank you for your attention. So this is very much the this work and this ongoing work, and I think it has educational value for students. And believe it or not, we teach statistics course and we still use the tables for probability and statistics. And because the special functions are not readily available, for example, in exams, they cannot use a special function because it requires access to the internet. But having a similar formula like this one, so it can avoid and overcome the difficulty of using tables. Thank you for your attention.
Thank you very much. That was a great talk. I really enjoyed that, Dr. Hamdi. Any questions from the audience?
There's one from Bertrand. Did you try to use your implementation for special functions that satisfy nonlinear differential equations?
I know I've read an article where they use the two-point Padé approximation for differential equations. So it's an interesting paper that I will give attention. And so the idea is if you have differential equation you can always find a Taylor series solution for the differential equation, and from it you can build a Padé approximation. And once you build the Padé approximation, then you can also like a boundary value problem, so apply it at one end from the interval and the other end. So the key idea is Taylor series. So all the behind all of this is the Taylor series. The key is the Taylor series, from which we obtain the Padé approximation.